Okay, hi. So here we will look at how to represent signals. So now what we have seen so far is the representation of a signal in the way is shown here. So a signal is either a function of time or it is a time series. So for example, this is useful for us to understand. For example, what happened when. For example, in this representation in the figure, you can see that in for this continuous time signal x of t, you can see that this signal has see three peaks at times t1, t2, and t3. Okay, so this representation is generally what we call as the time domain representation of the signal, because it is useful for us to know what happened when. Okay, but this representation might not be helpful in all situations. So there is an alternate representation which we can use. Now for example, will make a signal using the alternate representation. So for example, consider the three sinusoids like this: zero point 0.3 sine omega 1t, x2 is 0.6 sine omega 2t, and x3 is 0.1 sine omega 3t. Okay, so there are three sinusoids at three different frequencies. Now, if you suppose you add these three and get a new signal, x of t is equal to x1 of t plus x2 of t plus x3 of t, you might get a signal like this. So this may not be exactly the sum of these three. I just drew this to illustrate the idea. So now, what we just did now is we have actually done the reverse of Fourier analysis, because the objective of Fourier analysis is that we are given x of t, we should find out what are the constituent signals that make up x of t. So in Fourier series, these constituent signals are sinusoids. Okay. So for example, this x of t here in this case is 0.3 sine omega 1t plus 0.6 sine omega 2t plus 0.1 sine omega 3t, and the alternate representation I said is what we call as the spectrum representation, or you can also call it the frequency domain representation. So the spectrum representation looks like this, where you can see that there are three frequencies. Like the signal x of t consists of three separate frequencies, the constituent frequencies of x of t, which are omega 2, omega 1, and omega 3. The strengths of these are respectively scaled by the strengths in the time domain. Okay, so this is 0.3. X2 is x1 is 0.3, x2 is 0.6, x3 is 0.1. So correspondingly, those similar amplitudes are there in the frequency domain representation also. Okay, so this is an alternate way of representing the same signal x of t. So why do we want this alternate representation? That really depends, because there are many other signals, there are many signals which can be analyzed better in the frequency domain. Okay, for example, music, for example. Okay. A lot of times we are able to discriminate and enjoy music because we are able to perceive different frequencies. Whenever our ears are continuously doing this kind of Fourier analysis, whatever sounds is falling on our ears are constantly performing the decomposition of the input sound into various component frequencies, and it is passed on to the brain to understand how what is the sound, what is the sound. Okay, so and there are also a lot of mathematical properties which make many systems easier to analyze in the frequency domain. So if you get a frequency domain representation of a signal, the interaction between that signal and the system is easier, in many cases easier, when we represent both the system and the signal in terms of its frequency representation.